curve. These are enormous, so the curve is very, very gradual. So the cornering is very, very gentle, so they can go really, really, really fast. They go around millions of times every second, so the kinetic energy really, really builds up. They get to something like 99.99999% the speed of light, something like that. And then they smash together. Sometimes there's a stationary target, and sometimes they have these particles going around in opposite directions and they collide. There's a huge amount of kinetic energy involved. Now these are inelastic collisions, if you remember from Unit 1, which means that the kinetic energy afterwards is a lot less than the kinetic energy before. Unsurprisingly, things are smashed together. Even when car crashes together, the kinetic energy afterwards is less than the kinetic energy before. But in this case, this kinetic energy doesn't disappear off in like heat and sound and physical energy, like in a car crash. It converts to mass energy. So what's involved in that? The mass energy shows itself as particles coming out of nowhere. Well, they're not coming out of nowhere, they're coming out of the kinetic energy. And these particles are fundamental particles. And fundamental particles are, this is the definition, they are not themselves made of anything smaller. Now there's two families of fundamental particles. There's quarks and leptons. There's 6 types of quark: top, bottom, up, down, strange, charm. There are 6 types of leptons: electrons, muons, taus, electron neutrinos, muon neutrinos, tau neutrinos. This is a bit of a geography lesson, I'm afraid. In other words, it's just kind of learning names and kind of regurgitating names. But unlike geography, this is a lot more interesting. So quarks started popping out. Now, in the early particle accelerators, it was singular quarks and singular leptons. But as we made the particle accelerators more and more and more energetic, bigger and bigger and bigger particles made up of these things can appear. Now, the bigger composite particles, which started appearing from very high energy particle accelerators, they're not fundamental particles. Fundamental particles are particles like we saw before, which are not themselves made up of anything smaller. So if you've got particles which are made up of smaller ones, then they are not fundamental particles. Again, where do these particles come from? They look as though they suddenly appear in the particle accelerator, but they don't suddenly appear. It's because they come from the kinetic energy loss, because it's an inelastic collision. Now here's the exchange rate, if you like. The kinetic energy lost goes into mass energy. Now the formula involved in the mass energy is E equals mc squared. So if we rearrange to make m the subject mass, then we get m equals E over c squared. So the higher energy the particle accelerator, the bigger and more interesting particles which start appearing. And yeah, the bigger and bigger the composite particles, the more and more interesting they are. These big composite particles, they don't last long. They decay away. They break up into individual quarks really pretty quickly. But the bigger and more exotic the particles, the more interesting they are. And so this is why we want really high energy particle accelerators. More of the geography lesson. You've got to know these terms. So composite particles, the generic name for composite particles are hadrons. Now we need to say immediately that composite particles are only made of quarks. The lepton family, so that's electrons, muons, taus, electron neutrinos, tau neutrinos, and muon neutrinos, these do not like being together in any way, shape or form. They obey the Pauli exclusion principle, whereas quarks do like being next to each other. They're a lot more sociable. So there are 2 families of hadrons. There are baryons and there are mesons, or some people call them mesons. Now baryons are composite particles made of 3 quarks. There are 2 stable baryons. One baryon composite particle is called a proton, and this is made up of an up quark plus an up quark plus a down quark, and the other composite particle, which is stable, is neutrons, and that's down quark plus up quark. Why do we need to know this? Well, if you want to work out the overall charge, the overall electric charge of a composite particle, then you add up the electric charge which the individual quarks have, and you'll always be told what electric charge the individual quarks have. So these are the only stable ones. Stable meaning the ones which don't disintegrate or decay. So these are what make up our world, along with electrons. There are other baryons which get made in particle accelerators, like sigmas, deltas, omegas, but these disintegrate. They decay really quickly. They decay into smaller things like quarks, so they don't stay as particles for long. So we don't really see them in everyday life, because if they were made, which they're not made very often, but if they were made, then they sort of break up into fundamental particles really quickly. Mesons or mesons, there are no stable mesons. This is why we haven't seen mesons in everyday life. They are made from a quark and an anti-quark pair. So examples of mesons are pions and kaons or kaons, or however you say that, but there are no stable mesons. So the quarks and the leptons, and obviously the composite particles which the quarks are made of, these make up matter, and these are called fermions. So the next question is, well, what other particles are there? Well, there are these other particles, and these are the force carriers. So there are some fundamental forces, and fundamental forces are the gravity force, the weak nuclear force, the strong nuclear force. I put gravity twice, haven't I? What I mean to say here is electromagnetism. We talked about electromagnetism already. Electromagnetism is the origin of electric forces and magnetic forces. Let's get rid of this. This is green, not blue. I do apologise. Electromagnetism. There we go. So what is gravity? You know what gravity is. It's a long-range attractive force between particles which have mass, and gravity is actually very, very weak. You've got to have masses which are like the size of planets in order to get big enough forces to actually do anything with. The weak nuclear force, we'll talk about that when we talk about nuclear decay, but the weak nuclear force allows protons to turn to neutrons and neutrons to turn to protons in radioactive nucleuses. And you might say, well, what the hell is the use of that? Well, the turning of neutrons into protons and protons into neutrons is how beta decay happens, and beta decay is a really important stage in the nuclear fusion process in stars. So if it wasn't for the weak nuclear force, then beta decay wouldn't happen, and if beta radioactive decay didn't happen, then stars wouldn't shine. So we don't see this much on Earth, but we get the benefit of it from the sunshine, which everything in life depends on, and stars absolutely need the weak nuclear force to work. The strong nuclear force is what keeps the nucleus together. If you think about the particles in a nucleus, there are neutrons and protons. Protons repel, so every nucleus really wants to blow itself apart and disintegrate. So you have like a hula hoop or a belt around the outside, and that's the strong nuclear force. Electromagnetism, or electromagnetic force, this is all of electrical forces and all of magnetic forces. So, as we said before, all of chemistry, molecules attracting, repelling, sharing electrons, swapping electrons, bonding, all the rest of it, fire, all these chemical reactions happen because of the electromagnetic forces. All of electricity happens because of electromagnetic forces. Your body runs, all body signals run on electricity. So you see because of electrical impulses, you move because of electrical impulses. You touch stuff, we've talked about it. It's a response to the electrons repelling each other. So we really, electromagnetism is what dominates our world, our experience of world, apart from the tendency that we fall over when we trip because of gravity. Anyway, these things, sometimes you can describe them with force fields, for example, gravity force field, or electric field, or magnetic field. But particle accelerators have shown us that there are actually also particles associated with these guys. The particles associated with these guys are called bosons. So the particles which are associated with gravity are gravitons. It's worth saying these haven't actually been discovered in reality yet, but we're pretty sure they do exist. The weak nuclear force is associated with W and Z bosons. The strong nuclear force is associated with gluons, and the electromagnetic force is associated with virtual photons. The reason it's virtual is that you don't actually see these photons. So if you think of like approaching a magnet with a fridge magnet, and you feel that force of attraction when the fridge magnet is really close, you don't actually see photons of light being exchanged between the magnet and the fridge door. It's happening, but you don't see it. That's why it's virtual. I don't know why I've not put these in the same order as that, but hopefully you can cope with it. Gravity associated with gravitons, weak nuclear force associated with W and Z bosons, strong nuclear force associated with gluons, kind of glues it together, that kind of makes sense, and electromagnetic forces associated with virtual photons. You're doing well, by the way. I know I keep saying this is like a geography lesson, kind of learn stuff. But we're almost there with this video. So what the hell is the point in all of this? This is what non-physicists, this is a criticism which non-physicists quite often level at the whole particle accelerator stuff. What the hell is the point in this? Well, actually, although CERN and other high energy research physics stuff is the sexy stuff, actually the physics stuff is only a tiny proportion of all the particle accelerators in the world. Linear accelerators, we've touched on this before, are little linear accelerators are used to make X-rays. So yeah, little linear accelerators make X-rays, and like millions of X-rays are taken every year for medical reasons, aren't they? There are loads of uses of X-rays. So there's X-rays used industrially, things like cargo planes and trains or whatever are X-rayed to see what's inside them, to make sure things aren't smuggling. So whenever you have X-rays, there will be a linear accelerator involved. Cyclotrons, we've always said cyclotrons are really compact. They get really high energy stuff, usually protons, and pretty much every hospital will have a cyclotron in it for this thing called proton beam therapy, which is a way of killing cancer. Also, you can make artificially radioactive elements like cobalt, and well, cobalt is naturally occurring, but you can artificially make radioactive isotopes with cyclotrons, and you can also make elements like technetium with cyclotrons. Why do you want to do that? Well, traditional radiotherapy, where you bombard cancer with radiation from a lump of something which is radioactive, that lump of something which is radioactive is made in a cyclotron. So cyclotrons are crucial for medical treatments, and they have saved millions of people. So let's go back to this big physics stuff though, the synchrotrons, things like CERN in Switzerland. What the hell is the point in this? Well, with a tiny number of particles, now these particle accelerators only deal with like a relatively small number of particles, you whiz them round and round and round and round and round, give them so much kinetic energy that you actually recreate the conditions a very small, like nanoseconds after the Big Bang. So you whiz them round and round and round, you smack them together, and these are the conditions like nanoseconds after the Big Bang. Obviously we don't know what happened at the exact moment of the Big Bang, but we are now knowing what happens like we said, nanoseconds after it. And then this lets us understand how the whole universe then cooled and expanded. And once we get a much better idea of this, then we can understand how like maybe other universes cool and expand and get formed. So this is big scale cosmology stuff. The other thing it allows us to do when we're looking at things like gravitons, what we've talked about before, this is getting us towards, is helping us towards the idea of like a quantum theory of gravity, understanding gravity at the scale of really, really small. And once we understand the quantum theory of gravity, then we can understand black holes. And once we understand black holes, we know what's at the middle of black holes, and all of a sudden everything starts getting very, very interesting. So understanding how exactly our universe ended up from the Big Bang to what it is now will let us work back and work out what the hell a Big Bang